Another example, we're going to do a 3 by 3 matrix just to show how explicitly how this extends into higher dimensions, higher numbers of equations with more functions. This matrix is going to give us an equation y prime equals ay, and that equation would be of this form. Okay, y prime, y is going to be the vector with scalar components y1, y2, and y3, so that the derivative will be y1 prime, y2 prime, y3 prime, and that's going to equal this matrix multiplied by the y vector itself. And we can easily verify that if we multiply this row by y1, y2, y3, we get this. Multiply this row by y1, y2, y3, we get this. And this last row gives us this. So that this matrix represents this equation with this convention. Now we, as before, and as we generally do, we assume a solution of the form e to the lambda t times x. In this case, x is going to need to have 3 components so that our y vector will be a vector with 3 components, a 3-dimensional column vector. And that's going to be then x1, x2, x3. So we're assuming a y of this form. Without going through the details, this leads us to a minus lambda I, and remember that we derived this for an arbitrary number of components here, a vector of arbitrary length, column vector with n components, so it's certainly going to apply, anything we did there is certainly going to apply to a column vector with 3 components, so that our a minus lambda I vector is going to be 5 minus lambda, 2, 3, 3, 6 minus lambda, negative 7, 0, 0, 2 minus lambda. The determinant of a minus lambda I equals the determinant of this matrix, and without going through the details of calculating the determinant, we're going to get 5 minus lambda multiplied by 6 minus lambda minus 6 multiplied by 2 minus lambda. Now if you calculate this determinant, you might do it in slightly different order. Don't worry about how I got this. If you understand determinants, you'll understand I just expanded along the bottom row. And that should equal 0. Now this factor here, 5 minus lambda times 6 minus lambda is lambda squared minus 11 lambda plus 30, but then when we subtract 6 we get plus 24. That's multiplied by 2 minus lambda, and that's equal to 0. This factors, and remember, if it doesn't factor we can always use the quadratic formula, but in this case it factors into lambda minus 8 times lambda minus 3 times 2 minus lambda equals 0. So we get 3 solutions. Lambda 1 equals 8, lambda 2 equals 3, lambda 3 equals 2. Each of these eigenvectors should give us, each of these eigenvalues should give us an eigenvector. Using lambda 1, our matrix becomes, well, our matrix equation now will be a minus lambda I times x equals 0. That equation is going to become 5 minus 8, which is negative 3, and then 2, 3, 3. 6 minus 8 is negative 2, negative 7. 0, 0, 2 minus 8 is negative 6. Multiplied by x1, x2, x3 should equal the 0 vector, which I'll write out as 0, 0, 0. This is equivalent to the system of equations minus 3x1 plus 2x2 plus 3x3 equals 0. 3x1 minus 2x2 minus 7x3 equals 0. And negative 6x3 equals 0. That's actually going to be very easy to solve these equations. You notice that none of these equations is a multiple of any of the others. Now it turns out that either the first two equations can be written as the other equation plus a multiple of the last equation, but we're not going to bother with that. We're just going to see that x3 is 0, which makes these two terms 0, and that reduces us to the following: x3 equals 0, negative 3x1 plus 2x2 equals 0, and 3x1 minus 2x2 equals 0. And look at what we've got. Two equations, degenerate equations, equations that are multiples of one another. And we then determine that, let's say x2 is 3/2 x1, so that our vector x1, x2, x3 could be written. If we choose x1 equal to 1, x2 is going to be 3/2. Let's not have fractions. Let's choose x2 equal to 2. So 3/2, let's choose x1 equal to 2. So that 3/2 of x1 is 3. So that x1 is 2, x2 is 3, x3 is 0. This gives us an eigenpair 8, 2, 3, 0. Now, our eigenpair 8, 2, 3, 0 implies a solution it doesn't equal, it implies a solution e to the 8t times the vector 2, 3, 0. Now we can repeat the process with eigenvalue lambda 2 equal to 3, and I'm just going to go ahead and write that down off camera. So again, lambda 2 equals 3 yields the following, and from that we simply subtract 3 from each of the diagonal elements, and we get changes in the diagonal elements. All the other elements of the matrix stay the same. This matrix multiplied by the x1, x2, x3 is going to give us the 0 vector, yielding the three equations we see here. This times this gives us the first equation, set equal to 0. Second row times this column, set equal to 0, gives us the second equation. Third row gives us the third equation. As before, we find that x3 has to be 0, and once x3 is 0, these two terms fall off. We just end up with 2x1 plus 2x2 equals 0, 3x1 plus 3x2 equals 0, the equations being multiples of one another, with solution. A solution is x1 equals negative 1, x2 equals 1. So that here's a solution giving us the eigenpair 3, negative 1, 1, 0, and solution e to the 3t times negative 1, 1, 0. The solution follows and with very completely analogous steps to the preceding. Now, lambda 3 equals 2 does throw a little bit of a curve at us, so let's see how that works out. Subtracting 2 from each of the diagonal elements in our original matrix, we get this, and gives us the bottom row here being all zeros. Well, 0, 0, 0 times x1, x2, x3 equal to 0, doesn't give us any information at all. Whatever x1, x2, and x3 are, if we multiply by the row 0, 0, 0, we are going to get 0. This leaves us with only two equations, 3x1 plus 2x2 plus 3x3 equals 0, and 3x1 here, 4x2 here, minus 7x3 here equals 0. Where does this leave us? Well, it leaves us with two equations and three unknowns. Meaning, among other things, we could choose an arbitrary value for one of these x1, x2, x3 and solve for the other two. But we're going to proceed just a little differently, and we're simply going to eliminate a variable from these two equations, which would be our natural instinct in this situation. If I reverse the signs of either of these equations and add the result to the other, x1 is going to go away, so I'm going to do that. You probably can't see what I've written here, but it's negative 1 times the first equation plus the second equation gives us this. Because negative 1 times the first, the 3x1s will go away. Negative 2 and 4 is 2. Negative 3 and negative 7 is negative 10, 0 and 0, 0. So we end up with 2x2 minus 10x3 equals 0, which can be written easily enough as 2x2 equals 10x3, meaning that x2 equals 5x3. Choosing x3 as 1, we get x2 and x3 being constrained, so that if x3 is 1, x2 has to be 5. So this is a solution, and it doesn't matter what number we put in here. We're still going to have a solution. It doesn't matter what x1 is. If we add negative 1 times this plus this, it's not going to matter. We're still going to get the same thing, so that I could just call this, let's say, A times A 5, 1, where A could be any number. Now, getting things out of place a little bit, our eigenpair for this is 2 A 5, 1, leading to solution e to the 2t times a 5, 1 for any value of a. We'll summarize this in a subsequent brief clip.